Good afternoon, everyone. My name is Marielle Magtibay, and I'm from the University of Waterloo. And today I'll be presenting to you about the design of a hybrid renewable energy system for a Northern Ontario community. Now, before I dive into the presentation, I first want to define what I mean when I say a hybrid energy system. It's basically an energy system consisting of two or more sources of energy. So in this specific case, I will be talking about hydropower, diesel generator, and then hydrogen energy system storage. I also want to acknowledge our mentors for this project from the University of Waterloo, listed here. Just a brief outline of my presentation. First, I'm going to talk about the motivations behind the project as well as our design goals. Give you a brief background on the selected community of Fort Hope, Ontario, go through our methodology, and as well as discuss the renewable energy resources and energy storage systems that we considered for our design, alongside some results and discussion, and finally some conclusions and recommendations. So Canada currently has approximately 175 off-grid communities across the country. And most of these communities rely on only diesel generators as a source of their electricity. Now, this is problematic for a number of reasons. First is the socio-economic concern due to the high cost of diesel fuel as well as the transportation of the fuel to these remote communities. The fluctuating diesel prices can also impact the long-term community planning, as well as the energy restrictions in the community places them under load restrictions, which can hamper the quality of their life as well as hinder local economic development. There are also some concerns on the health and environmental impact. So first is the diesel generator emissions. So this contributes to climate change as well as impact human health due to the particulate matter emissions from the diesel generator. The transportation of the fuel also increases the risks for spills and accident, as winter ice roads or flying the fuel over to the remote communities are really the only way of transportation for the fuel. Now, the objective of this design and analysis was to evaluate the application of a renewable energy in a hybrid system for a selected off-grid community. Our goals were to achieve a design that can result in over 4,000 tons of greenhouse gas reductions over the life cycle of the system, reduce the energy cost to less than 39 cents per kilowatt hour, and achieve a renewable energy penetration of at least 30%. So the selected community of Fort Hope is located 360 kilometers north of Thunder Bay, and they have a population of around 1,400 people. The existing energy system at Fort Hope consists of 4 diesel generators of different ratings, and they have a peak of approximately 990 kilowatt. And their diesel fuel consumption, based on a study done in 2007, also resulted in an O&M cost of $1.58 million per year. And their greenhouse gas emissions were also around 3,400 tons for the year. So moving on to our methodology. First, we modeled the energy consumption baseline profile of Fort Hope, and then we evaluated the available renewable energy resources that's available at Fort Hope. We also selected and sized different energy generators as well as the energy system storage, and we modeled the system's behavior on a tool that I will talk about later on, and then we also completed a financial assessment and verified the result using another tool. So the tools we used in this design was primarily HOMER, which stands for Hybrid Optimization Model for Electric Renewables. We used this primarily to do simulations, optimize the system, as well as perform sensitivity analysis. We then used RedScreen, which is developed by Natural Resources Canada, to validate the results that we got from HOMER. And lastly, we used HydroHelp to design our hydropower facility, and mainly in turbine selection. So what we have here is the energy baseline profile throughout the year that we modeled on HOMER for Fort Hope. Since we could not collect actual consumption data from the community, what we did was used the consumption profile of Casabonico Lake First Nations and scaled this by using the ratio of Fort Hope's peak load to the ratio of peak load of Casabonico Lake First Nations. And this baseline profile resulted in emissions of around 3,800 tons per year, and the levelized cost of electricity is 39 cents per kilowatt hour. And this is essentially what we'll be comparing our final design results with. Moving on to the renewable energy resources we considered. First was solar. We found that Fort Hope had an average installation of around 5.9 kilowatt hour per meter squared, ranging between 2.8 to a maximum of 8.7 kilowatt hour. However, due to the low capacity factor and also very high capital cost, solar energy was not further considered for our design. We also took a look at the wind energy resources available at Fort Hope, and they had an average at 30 meters of around 4.25 meters per second. And typically in a utility application for wind turbines, it's recommended for the minimum to be around 6 meters per second, which clearly Fort Hope does not observe even at its peak of 4.63 meters per second. So we further investigated other implementations of wind turbines across North America, and we found that there weren't really any suitable wind turbines that are currently being manufactured for the wind speed at Fort Hope, as we can see in this figure. So wind energy was also not considered for our design for later on, since the financial cost of investing for the wind turbine was not justified enough by the wind speed at Fort Hope. So Fort Hope is also located near Albany River, which makes hydropower a viable renewable energy source for the community. What we have here is the flow data, and we were only able to find data available from May to September of the year. So what we did was we had to extrapolate it by scaling the flow of gauge locations downstream of Fort Hope. And we found that the annual average flow was around 40 meters cubed per second, and we estimated the head to be very low at 3 meters to give us the worst case scenario for our model. Now for our energy storage systems, we considered using flywheel, compressed air, pumped hydro, different kinds of batteries, so like vanadium flow battery, lead acid battery. And how we selected our energy storage system is by creating a decision matrix with criteria such as the operating cost, the impact of the components and materials, total cost, the physical footprint, and the carbon dioxide production intensity. And in the end, a hydrogen system, hydrogen energy storage was selected. So what we have here is the equipment summary of what was considered for our model on Homer. So we have our existing diesel generators that the community already have, a Kaplan gear turbine for a hydropower facility, and our hydrogen energy storage system consisting of a storage tank, your fuel cell, and electrolyzer, and finally a converter. So in our modeling, the optimal design consists of a 636 kilowatt run-of-the-river hydro, 2 of the diesel generators that already exist in the community, and its sizes are at 650 kilowatt and 375 kilowatt. We also have a 150 kilogram hydrogen tank with an 80 kilowatt electrolyzer and a 100 kilowatt PEM fuel cell. We also have an 80 kilowatt converter. Now comparing our model results to our design goals, we found that our design resulted in 50,000 tons over 25 years of greenhouse gas reductions. We achieved a levelized cost of energy at 24 cents per kilowatt hour, and our renewable energy penetration was at 54%. So in our system, the hydropower was used as a base source supply, as we see in the lighter blue on the energy profiles. The diesel generators were then used as an intermediate load following system. So as we see on the winter day profile, as the electrical consumption decreases and increases, so does the 650 kilowatt diesel generator. The fuel cell is then used to provide supplementary power to avoid the usage of 650 kilowatt during the kilowatt diesel generators during times of low demand. For example, during the summer here, we see in red is the fuel cell providing supplementary power for the 375 kilowatt diesel generator. And during the summer months as well, the excess electricity provided by the hydropower is stored as hydrogen. So what we have here is our hydropower output. We had a design flow rate of 30 meters cubed per second, and our mean output for the hydropower facility was around 356 kilowatt, up to a maximum of 540 kilowatts. Now, between the months of February and April, we see a zero output, and this is due to the Albany River's flow reversal into a lake nearby Fort Hope. And our capacity factor for our hydropower system is at 56%. Now, for our diesel generators, both of them were operated around 91% of the year. If we look at the figure above, that's for the 650 kilowatt diesel generator. We see that it is not operated during the summer months and running into the fall months as well, and this is due to the lower electrical demand from the community. However, we see that the 375 kilowatt diesel generator is operated throughout the entire year. And the operating schedules of both the diesel generators results in diesel fuel consumption reduction by 756,000 liters per year, or a 54% reduction compared to the baseline model. Here we have the fuel cell output for our system. It has a mean output of around 44 kilowatts and an efficiency of 50%. We see that the output is mainly during the summer and the fall months, and as I said before, this is to supplement the 375 kilowatt diesel generator. The fuel cell contributes around 1% of the total system production of energy. Now, for our hydrogen storage, we selected a tank of size 150 kilograms, and the system is able to produce around 3,144 kilograms of hydrogen per year. It basically has the capacity to hold 5,000 kilowatt hours of energy. And given an average load of 594 kilowatts, we have a tank autonomy of 8.4 hours, which means you can run the electricity just using hydrogen for that long. Now, since the design flow rate is really a function of the river flow that's available for Fort Hope, we performed a sensitivity analysis on the design flow rate. And as expected, the hydro capacity increases with increasing design flow rate. However, if we take a look at our net present cost, we see that it reaches the minimum at our design flow rate, which is at 30 meters cubed per second. And the reason for the net present cost rising as the capacity increases is because the capacity factor basically decreases, so your actual output from the facility decreases, so you're having to use more diesel fuel, which is why the cost starts to increase after 30 meters cubed per second. We also modeled our system on another tool called Red Screen. We discovered that these tools model the hydro resource differently, as well as the hydrogen energy storage system. But the main takeaway here is that their total system power output deviated by only 2%. So this basically validates the results that we got from Homer. For our financial assessment, the levelized cost of energy is around 24 cents per kilowatt hour. The capital cost, $4.6 million. The O&M cost, $990,000. And the total net present cost at $17 million. And assuming a 6% annual discount rate, there's a 22% return on investment when we compare the cash flow of this, our proposed system versus the existing diesel generators. Now, since financial cost is one of the major barriers for renewable energy systems, we should really take a look at the financial opportunities available for us to be able to implement these kind of projects. So, for example, you might be able to get 30 to 50% off your capital costs under the tax regulations and Canadian renewable and conservation expenses. The Aboriginal Affairs and Northern Development Canada also has a program, Eco-Energy Program, which can provide up to $250,000 for feasibility studies. We should also take a look at the opportunities for communities to get revenue based on the carbon credits that they could gain from decreasing their fuel consumption. And lastly, to further lower the cost, we should also invest in research and development to improve the efficiency of the system. Now for our conclusion, basically we met all of our design goals with a 636 kilowatt hydropower system, a 650 and 375 kilowatt diesel generators that the community already has, a hydrogen energy storage system of 150 kilograms and a 100 kilowatt fuel cell. And we saw that our design was able to achieve a reduction of 2,000 tons per year for greenhouse gas emissions, have a renewable energy penetration of 54%, and a levelized cost of energy of 24 cents per kilowatt hour. And we achieved our design by collecting the natural resources data available at the community, assessing the feasibility of different renewable energy technologies, and modeling the baseline as well as the behavior of the proposed system on Homer. And we validated this result using ResGreen, and we saw a 2% total output deviation. For our recommendations, specifically for the community of Fort Hope, we would recommend the collection of actual river flow data to ensure that your design of the hydropower system is appropriate for the community, as well as a study on the consumption patterns before and prior to installation, again to ensure that your system meets the community's needs. And for just general recommendations for the design of renewable energy systems for remote communities, we should quantify human health impacts of the diesel generators in the remote communities so that we can justify the implementation of these types of projects. And lastly, it's recommended to perform a financial sensitivity analysis with increased diesel costs, as well as look at the opportunities in a carbon credit economy for communities such as Fort Hope. And these are our references. Yeah.
Thank you very much, Marielle. So we still have a few minutes for some questions. I got one question, but I'm gonna have my question last.
Go.
Yeah.
Oh,
So you
okay.
feel free to start, or John. Or
Okay, start, John.
yes, would you like to?
So you identified one community in
Northern Ontario.
right, and then you use the data from another community.
Yes. So we were not able to collect actual data from the community. We basically scaled the data that we got based on the peak load of Fort Hope and the peak load of Casabonica Lake, which is the community we took the data from, and we just scaled it based on their peak loads.
Yeah, that was really good, because if you can't get it, then it's
Yeah.
yeah, I just wanted to clarify that.
Yeah, that's a very interesting project as well. And I wonder, what are the parameters that you have to play with in order to improve efficiency?
Okay. So for modeling the energy generators on Homer, the parameters you play with are basically your fuel rate consumption, right? So how much diesel you need to produce a kilowatt hour for the community. Also the efficiency of, really, you can input the efficiencies of different systems. So you can take a look at improving your electrolyzer efficiency, your fuel cell efficiency, and in addition, the diesel generators as well.
With lower cost, this is the important thing.
Yeah, and I have one question for you. How you will see the effect of following up safety standards for such projects?
Okay, so we actually performed a health and safety assessment. I just didn't include it in the interest of time. So in terms of...
You did
We did it, but we just didn't include
Okay,
it
so
because-
tell us a little bit more about it.
So we focused on...
It's very interesting because you are dealing with high power, so.
Yeah.
So-
We focused on the hydrogen energy system storage, and based on a literature review we did, we found that the risks that were identified were mainly with leakage of hydrogen from your system, as well as possible combustion. But we found that with, I guess, rigorous maintenance of the system, that this could be monitored as well. And you could also locate your energy system storage away from a densely populated area, which really shouldn't be a problem for a remote community such as Fort Hope.
Yeah, that's fine, but did you follow any specific standards?
Oh, look at like specific standards developed.
Because you cannot keep it floating. I mean,
Yeah.
it's risky, but how you will estimate how much is this risk?
Okay.
You need to follow up standards, right?
Yeah, so what we actually, our assessment was based on a literature review that followed standards, so
Okay,
we
indirectly.
basically just worked it off from there.
Okay, thank you very much. That answered my question. Thank you very much. So any questions from the audience to any of the presenters? Please feel free. Yes.
Just a quick question. Actually, why did you pick hydrogen storage?
Oh, okay.
I was gonna
Because
say.
in my understanding, it's more expensive. Also, the efficiency is only like 30%.
So we based it on so we had a decision-making matrix, and we looked at the operating costs, the impacts of the components and the materials throughout its life cycle, as well as the operating costs. So the operating cost for this energy system storage is actually low compared to, for example, flywheel, where you have to keep the flywheel in like a vacuum to keep it spinning.
Yeah, but what about like rechargeable batteries or some other?
Oh, because of we considered the environmental impacts of those as well, right? So I guess we had a higher ranking for the impacts of the components, so that's why we ended up not choosing batteries that would be using toxic chemicals.
Any other question or comment?
Yeah, I do.
Yes, please.
You mentioned about the maintenance issue with regards to the hydrogen storage unit. What is the local capacity to maintain the system, or is it an expertise that has to be brought in on a routine basis?
Well, initially it would be, I would think that it would be an expert in the field to do this, and then to ensure that you have an appropriate transfer of technology to the community, then there would need to be some kind of technical training program.
Is there any cultural issues that one has to be concerned about with any of the technologies with the local community?
I would say always, there should always be a concern with regards to transferring the technology, and educating them appropriately to be able to use the technology. And that really depends on what community you go to, right? For this project, we were not able to visit the community or really have contact with anyone in the community just because of its remote location, and we didn't really have funding. But for definitely prior to implementation of these kind of projects, it would be recommended, of course, to engage the stakeholders involved and ensure that you identify whatever cultural barriers there may be.